great pleasure of introducing to you my friend, my colleague, and my mentor, Professor Kolb, who's visiting us from the University of Chicago, partly to be able to tell us about his interests in inner space, outer space connections, in quantum and the cosmos, and partly to enjoy the beautiful fall weather we're having here in Houston. It was snowing in Chicago when we left it that right. Yeah. But Rocky, in fact, is not new to the area. He's somewhat semi-local, growing up in New Orleans and moving to University of Texas Austin for his graduate studies. So he's not really new to Houston's heat. He moved on to do postdoctoral research at the Caltech University, followed by taking on an Oppenheimer Fellowship at Los Alamos National Laboratory, before eventually in 1983 moving to where he now resides, the University of Chicago and the Fermi National Accelerator Laboratory in Batavia, just outside of the University of Chicago. Since 1983, Rocky has held a number of positions at the university, including the chair of the Department of Astrophysics, the dean of physical sciences, the director of the KICT, the Arthur H. Condon Distinguished Service Professor, probably more. He's very renowned in the field of particle physics and cosmology, and he's going to be telling us about some of his work on the interface between the quantum, the elementary particles, and the cosmos, the universe on its biggest scales. Rocky is known in the field as an expert in the science, as well as addresses his work has addressed questions such as what is the origin of the excess of matter or antimatter, what is the nature of the mysterious dark matter, how were the light elements created in the hot conditions of the Big Bang. If you're interested in learning more about these things, in addition to Rocky's talk today, you can pick up his book, Blind Watchers of the Cosmos, Blind Watchers of the Sky, which is probably available on Amazon. It's true. Without further ado, let's introduce the What's Science.
Thank you, Andrew. It's a pleasure to be back in the great state of Texas. Spent 5 years in Austin, and I've actually been to Houston many times, and I always enjoy coming back. This is actually, I think, my first trip to Rice. I don't know why it's taken me so long to come here, but I've enjoyed it here, and it's really great to see the great field that's building up here, particularly in astronomy. And I think that astronomy is completely appropriate for Rice, because astronomers and owls are creatures of the night. So astronomy should be done here at Rice. So I'm going to talk about the inner space of the quantum and the outer space of the cosmos. So what do I mean by the inner space of the quantum? Well, the quantum determines the behavior of things on atomic and subatomic scales, and it's important for things in your everyday life: transistors, lasers, computers, semiconductors, quantum entanglement. All that is determined by the nature of the quantum. And quantum mechanics rules inner space, quantum theory, particle physics, string theory, etc. It's the world of the microverse. The outer space of the cosmos, what do I mean by that? Well, I am a cosmology. This is the Georgian spelling of cosmology. It's the study of a large-scale structure, the origin, the composition, and the evolution of the universe. And when I say the evolution of the universe, I talk about the evolution of matter, stars, galaxies, planets, etc., the evolution of the radiation in the universe, and the evolution of space and time. And the force that rules outer space is gravity. And our understanding of gravity today is based upon Einstein's theory of general relativity. Now, So I'm talking about the biggest things in the universe and the smallest things in the universe. And it's sort of interesting that humans are mid-size in the universe. Our scale of common everyday sensory experiences is about a meter. The smallest scales we can talk about sensibly today is 10 to the minus 26 meters. And the largest scales is 10 to the plus 26 meters. So our scale, the human scale, is the geometric mean between the largest and smallest things in the universe. And it's always remarkable when I reflect upon we're able to think about the smallest things and the largest things. And it gives me something to be proud of our species, because we do not directly experience the quantum world directly. You know, every time you use your cell phone or a computer, you do. We don't directly experience the quantum world. We don't directly experience the cosmic world. And we don't directly, in everyday life, experience relativistic effects of near light speeds. So our species, midway between the largest and smallest scales, have evolved to perceive reality not as it actually is. Reality is really the quantum world and the cosmic world, but we don't directly experience that. But merely we experience things as required for our survival in our environment. And it never ceases to amaze me that we, our species, has developed an understanding of the quantum and the cosmos. It's pretty remarkable. It's something, one of the few things that makes me proud of our species. So the interesting thing I find about the quantum and the cosmos, and one of the things that attracts me, is that there is a deep and profound connection between the quantum and the cosmos, between the largest things and the smallest things. The great naturalist John Muir wrote that when we try to pick out anything by itself, we find it bound fast by 1,000 invisible cords that cannot be broken to everything else in the universe. So at universities, there's departments of biology, department of physics, department of astronomy, department of chemistry, and we think these things can be neatly divided, but they're all connected. We can't understand one without understanding the whole. And I'll try to develop the idea that there is this deep connection between the quantum and the cosmos. So let me start with talking about modern theory of cosmology and the evolution of space and time. My friend Isaac Newton wrote in his great book, The Principia, about space and time. He wrote about absolute space and absolute time. He wrote that absolute space remains always similar and immovable, and absolute truth and mathematical time flows without regard to anything external. So in the Newtonian picture, our classical picture of space and time is fixed. There's nothing you can do to change it. So I think of space and time as, say, on a football field, you know, space is out there, the yard, you know, they call them yard lines, but it's actually yard line segments. I've never heard it correctly referred to, but it's a line segment, it's not a line. But anyway, it's painted on the field, and the game is played out on the field, but as it's played out, the space of the field doesn't change. And the same thing true with time. There's time that flows, and we think there's nothing we can do to change time. This view of space and time, this classical view of space and time, led to a cosmology based upon this Newton's clockwork universe, that everything is determined based upon his law of gravity and his laws of motion. Now, this all changed at the beginning of the 20th century with the work of Albert Einstein. And in 1905, he developed a theory of special relativity that related space and time. He didn't stop there, but he went on to realize that gravity is actually curved space. So in the Einstein theory of general relativity, his theory of gravity, space and time are not just absolute, but in fact, they are relative, and we can bend space and warp space. So this led, shortly after Einstein's 1915, early 1916 development of this theory of gravity, one of the first problems he addressed was the problem of cosmology. And he started with the idea that gravity shapes the universe. That's still true. He had a new theory of gravity, so he knew that he had a new powerful tool to try to understand the universe. In his theory, gravity is curved space. Now Einstein made an assumption, an assertion that the universe is static. Really wasn't based on any experimental observation, but he thought the universe should be static and unchanging, in the universe we see today should be the universe that existed in the past and will exist in the future. In order to accomplish this and to find solutions to the theory that he developed, he had to introduce something known as a cosmological constant. He had to introduce a new constant of nature in order to make the universe static. Now, at this point, I think for the first time, cosmology becomes a science. One of the hallmarks of science is that there are no authorities in science. The ultimate authority is nature, it's experiment and observation. So even the idea and theory and model of perhaps the greatest scientist of the 20th century was subject to experimental and observational verification. And in fact, it was shown that Einstein was wrong, and the person who showed Einstein was wrong was a basketball player. Not just any basketball player, but a basketball player of the last decent athletic team of the university. The 1909 National Championship basketball team. Chicago did a three-peat as national champions in 1909. They were national champions, and one of the stars on this great championship team you've heard of was Edwin Hubble. Now, I know this is, no, I lived in Texas. I know this is Texas. And you say, basketball? This is Texas. What about football? So let me brag a little bit about the great athletic tradition of the University of Chicago in football. Now, I looked through the records. Chicago's never played Rice in football, but we do have a common opponent in football, the University of Texas. Chicago's record against Texas, Chicago's unbeaten. It was 68 to 0 in 1904. Rice maybe not so successful. So anyway. So what Hubble discovered in 1929 is that space is not static and unchanging, but space is expanding. He showed that Einstein's model of the universe was wrong. And one of the implications of his discovery that the universe is expanding is that the universe is changing and evolving. It began with a bang. So the idea of the Big Bang is that our universe emerged from a state of high temperature and density 13.8 billion years ago last Tuesday, and is expanding and cooling, evolving and dynamic. universe visible today was once much smaller and much hotter. Okay, so this is a theory, it's a model, it's an idea. How can you be sure that the universe is expanding and evolving? That the universe was different billions of years ago than it is now? Well, astronomers have an advantage over our friends, the paleontologists, who talk about, you know, what the Earth was like 65 million years ago. Because astronomers have time machines. The time machines that astronomers use, some of them are familiar to you, they're telescopes. And I'll also try to talk about another type of time machine that's a particle accelerator. I used to work at a particle accelerator lab, but I'd like to tell people I worked at an atom smasher laboratory. That sounds like a particle accelerator. You have accelerators in your car. But to tell people I worked with an atom smasher, that sounds pretty cool. So the Giant Magellan Telescope in Chile, the South Pole Telescope, the Hubble Space Telescope, the Large Hadron Colliders, these are all time machines. Now, these traditional telescopes, it's easy to understand that why it's a time machine, because as you look out in space, you're looking back in time. When we look at the sun, we're seeing the sun not as it exists the moment we look at it, but as it existed 8 minutes ago, because it takes light 8 minutes to reach us from the sun. So we're looking back in time when we see the sun. If we, at night, look at a nearby star, we might be looking at the star not as it exists the night we see it, but as it existed maybe 10 years ago, because the star might be 10 light years away. Distant galaxies, we're looking back millions of years. The farther out in space you look, the further back in time you can see. So we can use time machines to look out in space and back in time and observe the universe changing and evolving. So now about the quantum and the cosmos. There are many subjects, many areas I could talk about the quantum and cosmos, but in the 3 hours remaining, I won't be able to talk about all of them. I would talk about dark matter and dark energy, but I could have equally well talked about cosmic inflation and the origin of structure, questions involving the quantum and the cosmos, like why is there a universe? Is there only one universe? Is there a multiverse? What about the space-time singularity at time zero, quantum gravity, origin of the elements? There are many subjects that connect the quantum and the cosmos. And I'll just talk about dark matter and dark energy. Now, the International Union of Pure and Applied Cosmologists require that I show this slide in every public lecture. This is a representation of the present composition of the universe, the present composition of the universe. And we learned several things looking at it. Today, most of the radiation in the universe is not visible to us, to our eyes, but it is in the microwave region. And there's a microwave background radiation. Although the universe was once dominated by the radiation at early times, today it only provides 0.005% of the total mass of energy in the universe. This diagram also illustrates why chemistry is not important. Sorry. The chemical elements, and by chemical elements, I say elements other than hydrogen and helium, make up only 0.025% of the mass and energy in the universe. Pretty insignificant. I don't know why we have chemistry. I used to think universities should have had chemists. Actually, but when I became dean, I appreciated the chemistry department because it was in my division. And now, I think that every university should have one chemist. So there's a much larger fraction of the mass and energy in the universe in the form of neutrinos, maybe about 0.17%. Neutrinos are elementary particles. You can imagine an electron if you can imagine an electron and take a very small pair of tweezers and pull out the electric charge, what would be left behind would be a neutrino. Stars that astronomers have been looking at for millennia, less than 1%. Most of the normal matter in the universe is in hydrogen and helium gas. That's hard to see. But 95% of the universe is dark and unknown. Dark matter making up 25% of the present mass and energy of the universe, and dark energy making up about 70%. So the universe is dark and spooky. There's dark matter and dark energy that we don't understand that makes up most of the universe. Now, dark matter and dark energy seem to be very different. Dark matter pulls things together, attracts attractive gravitational force. We don't understand what dark matter is, but I think the most likely explanation is that it is a new elementary particle species that has not been discovered yet. Dark energy has the opposite gravitational effect. It pushes things apart. It's like repulsive gravity. We don't understand dark energy. The most popular explanation is that it's related to intrinsic energy density and intrinsic weight of completely empty space. Okay, so October 31st, coming up, 2 weeks, is International Dark Matter Day. Everybody's excited about this, I know. So, my word to children, this is what we going to do to celebrate International Dark Matter Day. Children should dress as their favorite dark matter candidate, ring doorbells in the neighborhood, and all of the people who are very interested in dark matter will give them candy. So if they have children or no children, tell them to do this. It's really going to be a great day. Okay, so the fact that most of the matter in the universe you can't see is not a new discovery. It's been around for about 80 years. And 80 years of observations by astronomers have suggested that the beautiful images of galaxies that we see are only showing a small fraction of the matter in the universe. So this is a beautiful image of a galaxy taken with the Hubble Space Telescope. But if you ask, what would a galaxy look like if you could see dark matter, it would look much different. It would look something like this. The galaxy that you do see, it's just a small disk in the center, and it's surrounded by a halo of things that you don't see, but we deduce the existence of the dark matter by the gravitational effect that it produces, the gravitational force that it produces. So it's surrounded by a halo of dark matter, and there should be little subclumps of dark matter also. So this is really what a galaxy should look like. What is this dark matter? Well, we don't know, but we have an idea that early in the history of the universe, there was a new particle species that was produced from the primordial soup, the hot primordial soup of the Big Bang. So the picture is something like there was a bang, the time equal to 0, the temperature infinity in the extreme case. Then when the age of the universe was a billionth of a second AD, after the bang, and the temperature was 100 gazillion degrees. The hot primordial soup produced a new species of elementary particles that's stable and is around us today and consists of the dark matter. So why can't we build a big telescope and look out in space and back in time and watch the dark matter being produced. The problem is the universe only became transparent to light, to electromagnetic radiation, 380,000 years after the Bang. For the first 380,000 year history of the universe was so hot and so dense that we can't see through it with electromagnetic radiation. If only someone could think of an idea of a way to look back, maybe with gravitational radiation or something. Who knows? Something crazy like that. We might be able to understand this, but we can't look out in space and back in time and directly see the dark matter produced. Well, but there is something we can do. We can produce it here on Earth, maybe. And this is the idea that people are trying to see dark matter in Switzerland. Does it have holes in it, like Swiss cheese? We don't know. But the idea is that there are atom smashers in Switzerland that accelerate protons in the velocities very close to the velocity of light in one direction and the other direction, and they smash those puppies together and reproduce the conditions that were present when we think the dark matter was produced. So in Switzerland, today, we can reproduce the conditions in the universe a billionth of a second after the Bang. So this is an enormous machine. This is the outline of it. It's buried underground. It's outside of Geneva, Switzerland. This is the Geneva airport. You might be able to make out the Alps are back here. This is Lake Geneva, and the most of the city of Switzerland could fit inside a 17-mile circumference ring. So small, compact cities like Houston, could fit inside of this ring.
No.
So what is in this primordial soup? What were the conditions of the primordial soup? Well, let's imagine we have a can of primordial soup. It's a sample of the universe, 1 nanosecond AD, when the temperature was 100 million degrees. It was condensed. This primordial soup was really condensed. In 1 can of primordial soup would be 50 times the mass of the Earth in matter, 50 times the mass of the Earth in antimatter, and for reasons that we don't understand, there was an extra margin of matter. There was a little bit more matter than antimatter. Because as the soup cooled, this matter and antimatter annihilated, producing the radiation in the microwave background radiation, but there's a little bit extra matter that could not find an antimatter partner with which to annihilate. And that extra mountain of matter in every can of primordial soup is what's responsible for all of the matter we see in the universe. The soup was condensed, the soup was hot. Per serving of primordial soup is a total heat energy that would be produced by 10 million years of the total energy output. 10 million years. The sun's not going to live that long, but there's a lot of energy, thermal energy, per serving of the primordial soup. What were the ingredients? Well, you can look on the can. And per spoonful of primordial soup were all of the elementary particles that have been discovered. So the collider is the Large Hadron Collider is trying to detect WIMPs, trying to detect dark matter. And my colleagues who do these experiments saying looking for new particles is like looking for a needle in a haystack. In a collision of particles, it produces sprays of hundreds of particles. You have to sort through millions and millions of collisions looking for things. It's not simple like looking for gravitational waves. This is hard work. But this is even harder looking for dark matter, because not only are you looking for a needle in a haystack, you're looking for an invisible needle in a haystack. So how can you find an invisible needle in a haystack? How can you detect dark matter which does not interact with anything in the detector? Well, we can do it the same way that physicists in the 1950s, 30s, 40s, and 50s deduced the existence of neutrinos. Bananas are radioactive. Bananas emit 15 neutrinos per second. So I have a radioactive source here. Why did your mom tell you to eat bananas? Potassium. There's potassium in the banana, but there's also potassium-40, which is a radioactive isotope of potassium. And that decays, it beta decays, and there's enough potassium-40 in a banana to emit 15 neutrinos per second. If you eat the banana, you are emitting 15 neutrinos per second. And presumably later that day, you produce radioactive waste. So inside the banana, there's a beta decay, there's a neutron in the potassium-40 inside the banana, and that decays to a proton and an electron, and the proton and electron fly out. Well, that's okay, but what physicists noted is that a proton and electron can go in one direction. So its momentum would not be conserved. So if you have something decay, there should be equal amount of momentum going in this direction and that direction, and the total momentum produced should be zero. Some going positive, some going negative. So a physicist, Wolfgang Pauli, proposed that there is another particle that you don't see that's coming out of the banana, that's a neutrino, that's balancing the momentum. And this idea seemed crazy at the time. Pauli apologized for introducing it, but he was right, and eventually neutrinos were detected. So it's a similar thing that we can do at the collider. There's a proton and antiproton come in, it produces a spray of particles that are detected in the detector. But if you have an event like this, where all of the momentum goes in this direction and none in that direction, you might say, aha, there's dark matter produced that's going in this direction. So we are looking for dark matter at the Large Hadron Collider by reproducing the conditions that were present in the primordial soup. It hasn't been found as of 7:30 today. So the missing energy signal, the missing momentum signal would be an indication of dark matter. There's more to the dark side than just dark matter. There's dark energy. And dark energy is thought to cause the acceleration of the universe. Now, what do I mean by the acceleration of the universe? I talked about Hubble and his discovery of the expansion of the universe, and he came up with a law that's known as Hubble's law that describes the expansion velocity of the universe. And what Hubble did was to measure the expansion velocity today, or in 1929. But again, the farther out we look in space, the further back we look in time, and it's possible to look now it's possible to look out far in space, far back in time, and measure the expansion velocity at earlier time. A difference in velocity is an acceleration. Everyone expected the expansion of the universe to decelerate, that the universe is expanding, but the gravitational force wants to pull everything back together because gravity that we know of is attractive. But the surprise that astronomers found is, in fact, the universe is accelerating. Today, it's expanding at a faster velocity than it was in the past. What's causing that? This was such a surprise that the Nobel Prize was given to 3 astronomers for discovering the acceleration of the universe that's attributed to dark energy. Now, what is this mechanism that's causing the universe to accelerate? The simplest explanation goes back to Einstein's original 1917 paper, where he introduced something known as the cosmological constant. In 1917, Einstein proposed the cosmological constant to keep the universe from accelerating, to keep it from expanding. In 1929, Hubble discovered the expansion of the universe, and Einstein said, I don't need this cosmological constant after all. And later, he called the introduction of the cosmological constant his biggest blunder. He didn't know that 64 years later, astronomers would find evidence for the cosmological constant. So here's an important lesson. Never admit you're wrong. If Einstein had not said he was wrong, he could have been famous. He could have predicted dark energy. Okay, so how do we understand a cosmological constant? Well, the easiest way to imagine it is that nothing weighs something. That if you imagine a region of space with nothing around it, nothing. So think about nothing. I ask my students to think about nothing. Some of them are really good. They close their eyes and think. So imagine you have a region of space, conceptual experiment, and surrounded by a hollow metal sphere. And you can find a vacuum pump in the basement and you pump out all the air. You remove all of the matter, and you can cool, in principle, this metal sphere with nothing in it to absolute zero, so there's no radiation in it. What is left behind is something that we call the vacuum. Nothing. And if Einstein was right, and the cosmological constant is causing the acceleration of the universe, what's left behind is something that has a mass density of 10 to the minus 30 zeros with a 1, grams in every cubic centimeter of space. That's a really small number, but there are a lot of cubic centimeters of space out there. So this is a number that's small, so small, but it's not zero. This number doesn't make any sense. I don't know why it's called a cosmological constant. It should be called a cosmo-illogical constant. I think that's a better name for it. So this also connects to the quantum cosmos. How do we understand how nothing can weigh something? Well, what you have to do is to understand something I'm going to tell you. I'm going to tell you six secrets of nothingness. This is sort of the Zen part of this evening. 6 secrets of nothingness. Nothing is uncertain. Very profound. What do I mean by nothing is uncertain? Well, one of the fundamental ideas of quantum mechanics is something known as the uncertainty principle that Werner Heisenberg came up with in the 1920s. And he said that quantum mechanics has an inherent indeterminacy, an inherent uncertainty associated with it. And that there is an uncertainty in energy times an uncertainty in time has to be larger than some number H bar is constant divided by 2. So you can violate conservation of energy for a short amount of time. In fact, you have to. For a finite uncertainty in time, there has to be a finite uncertainty in energy. That's the first secret of nothingness. There's going to be 6 of these. Nothing is something. Something for us to remember. Nothing is something. So, although in this little hollow metal sphere I've removed all of the material and all of the radiation, what's left behind is quantum uncertainty. And Mr. Heisenberg tells us that at every point in space, because of the uncertainty principle, a particle and antiparticle can come out of the vacuum, existing for a brief instant of time and going back into the vacuum. So nothing is something. There's something to nothing. There's nothing to nothing. There's something like that. Okay, so if we visualize this, if you could see nature on microscopic scales where the world of the quantum operates, it wouldn't be a quiescent vacuum. It would be particles and antiparticles coming in and out of the vacuum, a seething froth of virtual particles. Nothing is something. Nothing has energy. So this seething froth of elementary particles, there's energy associated with that. Energy that we can calculate. So nothing is something, and nothing has energy. Not only does nothing have the energy of uncertainty, but there's another source. It has Higgs energy. Now, people talk about Higgs as the God particle. It was discovered in Europe. But at Fermi Lab, we didn't find the Higgs boson, but we discovered the Higgs boson. Right there. The Higgs boson. So the quantum vacuum has a Higgs potential. The Higgs potential is mass to electrons, quarks, and other particles. This Higgs potential energy is 246 billion electron volts at every point in space. 246 billion electron volts. That sounds pretty scary. Why aren't you electrocuted? There's 246 billion electron volts at every point in space. Well, we're only sensitive to potential differences. So if you had a Higgs meter and put one lead anywhere in the universe and another lead anywhere that's not in the universe, you would measure a potential of 246 billion electrons. Nothing has Higgs energy, nothing has uncertainty energy. I'm halfway through the 6 secrets of nothingness. Nothing is hidden. Very deep. My friends who are string theorists tell me that at every point in space, there are extra spatial dimensions. I don't have any friends who are string theorists. But if I did, they would tell me that at every point in space, there are extra dimensions of space that are wound up really tight and we can't see them. Well, there must be energy keeping these extra dimensions all wound up. Nothing is hidden. There must be energy associated with these hidden dimensions of space. 2 more secrets of nothingness. Nothing is mysterious. The problem with the cosmological constant is it's so small. We can calculate these contributions that we predict for the cosmological constant. These are theoretical predictions. And theories have never been wrong before. The theoretical prediction for the uncertainty energy is not infinity. It's infinity to the 4th power. Not such a good answer. So we work very hard and we can get it down to 10 to the plus 90 grams per cubic centimeter. Only 120 orders of magnitude too large. So we go back to our office, drink some coffee, drink a lot of coffee, sharpen our pencils, work harder, and the best we can do is get it down to 10 to the plus 30 grams per cubic centimeter. But it looks pretty good, 10 to the, well, except for a sign error. We want 10 to the minus 30 instead of the plus. It just doesn't make sense. This is the numbers that every number we can put our hands on is crazily large. Final secret of nothingness. Nothing matters. Something to live by. It is the energy density of nothing that will determine the ultimate history of the universe. If there's no nothing, if there's no, well, without dark energy, there are two histories, future histories of the universe. One could be that the universe expands, reaches a maximum size, and then recollapses into a big crunch. Another possible history is that the universe, without dark energy, would expand forever, decelerating, eventually at infinite time, coming to zero velocity. But if there is dark matter, then this universe will expand forever, ever accelerating in its expansion. And the universe will be a cold, empty space, a cold, empty place. The galaxies that we see today around us will accelerate so far away from us, they will be beyond our horizon, and we won't be able to see them. We will be alone in the universe. This is why we should do astronomy now, because those things are getting farther away. It's just getting farther. So these are the 6 secrets of nothingness. One of the 2 connections I talked about between the inner space of the quantum and the outer space of the cosmos. Now, I'd like to talk about some personal experiences I've had. So I'm a theoretical physicist. And I had an uncle who always would ask me, so what do you make? I said, well, I write papers. Okay, who buys the papers? Nobody buys the paper. I give them away to anybody who wants it. Not many people want it, but anybody who wants it, I'll give away my paper. Well, how do you make money? Well, they pay me to do this. And he just couldn't believe it. So why do we do this? Why do we care about the future of the universe, the past of the universe, how the universe works? It has no direct economic impact. But there is a quote I ran across the other day from a mentor of mine, Leon Letterman, who was a Fermi Lab director and Nobel laureate, who talked about how science can give us faith in the future. Leon wrote, basic research is designed to increase our understanding of the nature of the universe in which we live. It is curiosity-driven, unmotivated by thought of usefulness, and hence, almost by definition, it is not aimed at economic development. Scientists take up basic research out of a sense of pure excitement. It's really exciting. Out of joy and enhancing human culture, the joy that science brings is almost indescribable. Out of awe at the heritage handed down by generations of masters. The doing of science, as well as supporting of science, is an expression of faith in the future. Now then, my uncle would say, okay, so you're not making money out of it, but this physics you do, you're going to build bombs with it, right? It's going to contribute to our national defense. I had to tell him no, and I pointed him to a quote of another mentor and hero of mine, another director of Fermi Lab, Robert Wilson. In the 1960s, Robert Wilson was testifying before Congress trying to get money to build Fermi Lab. He was the founding director. And Senator Pastore, I believe he was from Wisconsin, asked him, is there anything here, that project, Fermilab, that puts us in a position of being competitive with the Russians? Russia used to be our adversary. And Bob Wilson could have said, oh yeah, we're going to build a dark matter bomb or a neutrino bomb, you know, we're going to contribute to national defense, but he didn't take the bait. He said it has nothing to do directly with defending our country except to help make it worth defending. A beautiful expression, I think. Okay, so what is the takeaway message that I would like you to have this evening? Is that we know a lot about how the universe works, but it's still cosmic mystery. 95% of our universe is a mystery. 95% of the universe is dark matter and dark energy. Now, I mentioned that I think that Einstein started modern cosmology about 100 years ago. How would Einstein have felt 100 years after he launched us in scientific cosmology that 95% of the universe is still a mystery? Einstein was a person of the 20th century, according to Time magazine. What would he have felt about 95% mystery? I think he would have been happy. Einstein said the most beautiful thing we can experience is the mysterious. To Einstein, it was the source of all true art and science. He thought that those to whom the emotion of mystery is a stranger are as good as dead. Their eyes are closed. Well, cosmologists today are no stranger to mystery. 95% of the universe is a mystery. We don't know how this mystery will be solved. We think it will arise from the connection of the inner space of the quantum and the outer space of the cosmos. I try to think about this every day. You know, I would wake up at night worrying about this. And, you know, I used to tell my wife I became keen so I could sleep at night, not having to worry about this, about these cosmic mysteries. But I have faith in the future. I know that somewhere out there, maybe in Houston, there's a child who has the courage and imagination and genius to solve our cosmic mystery. And this person out there in Houston will be the person of the 21st century. Thank you.
Thank you very much, Rocky. We have time for some questions. I want to start off by asking, how do I get into this International Union of Pure and Applied Cosmology? Would anybody like
to pay your union dues?
To me.
So I heard just a few weeks ago, the age of the universe shortened from 13.7 to 12 or whatever. What does that do to all these numbers?
Yeah, I think the age of the universe is 13.7 billion years. Now, we determine the age of the universe in various ways. One is looking for the oldest thing in the universe. And of course, the age of the universe is changing. You know, when I give a test to my students and I say, you know, how old is the universe? They say 13.78 billion years in 1 week. Where did you get that from? Well, a week ago, you told me. So anyway, I think the most reliable way to determine the age of the universe is through measurements of the microwave background radiation, and that's been consistent with 13.7 billion years. There's another way to determine the age of the universe, and that's measuring the present, to high accuracy, the present expansion history of the universe. So there's what we call tension between these different ways of determining the age of the universe. Of course, this will be eventually settled. But one of the things about astronomy is, you know, it's a relief. It's only 12 billion years old. You know, how do we imagine as humans 12 billion years? How do we as humans imagine 10 billion light years in distance? You know, the times, the distances. And also looking at the quantum, how do we imagine 10 to the minus 26 meters? You know, it's just so far beyond our human comprehension. So I'm not that worried about whether the universe is 13.7 or 12.7 billion years old. What's a billion years? Thank you for the question.
Thank you very much, Dr. Kolb, and welcome back to the great state of Texas. I've had the pleasure of visiting the Fermi Lab, and I noticed that many scientists kind of competed with different T-shirts with funny in formulas and things. You stated earlier that we do not directly experience quantumness or quantum physics, but aren't we in effect quantum beings, like our retina and things like that? There's quantum effects permeating our entire being. And so, are there ways, as a theoretical physicist, that you consider ways that we are experientially experiencing our quantumness?
Yeah, that's a good question. Thank you. So let me clarify a little bit by what I meant. I put the word directly in there. Quantum mechanics is really weird. No one really understands it. Well, I don't understand it, which means no one really. And but it's actually the way nature works. And so we do experience it every day. I don't have my cell phone on me, but if you use your cell phone, use a computer. Quantum mechanics prevents us. Most of what we see down here is actually empty space. It prevents us from falling to the center of the earth. It determines how we live, but we don't directly experience it in some way, and so it impacts our life. But you know, our species lived hundreds of thousands of years without knowing about quantum mechanics. And you know, I try to explain quantum mechanics to my dog. She doesn't care. But it's like I offer her a treat. Now solve Schrodinger's equation. No, she won't do it. So for our survival, we really have to know the Schrodinger equation. We don't have to understand entanglement for our survival.
What is it that gives us confidence that quantum mechanics, as we understand it, actually applies in extreme conditions of the early universe? How do we know it doesn't break down?
Yeah, well, that's a good question. Well, in some sense, the conditions of the universe, say, that are reproduced at CERN, we can study whether quantum mechanics works there. And if it's the same physical conditions in the early universe, we think, since we're reproducing it here, it should work in the early universe. Now, no, K-N-O-W, is a word that scientists should use very carefully. Do I know that it worked then? Well, I wasn't around, and if anyone was around, I can't find them to ask whether it worked then. But just because something is far away, either in time or in space, doesn't mean that we can't, with some confidence, speak of it, if we understand the physics. For instance, I can tell you, maybe I can't, but someone can tell you what the temperature on Mars will be in 3 weeks to a higher accuracy than predicting what the temperature in Houston will be in 3 weeks. Well, Mars is pretty far away, but the physics there is simple. Not much of an atmosphere. It's something that we understand. So it's a good question, and it's something that scientists test, and people come up with ideas that, well, maybe the speed of light changes with time. Maybe the charge of the electron changes with time. How would that change observation? So we're constantly probing and testing it.
You were saying that we have come up with two different values for the Hubble constant. One using the cosmology of the cosmic microwave background, the other using measurements of type 1A, supernovae, and Cepheus. And I read an article about this, and then I thought, well, it's possible that both numbers are right, because perhaps 380,000 years ago, when the universe became transparent, there was one rate of expansion. But today, perhaps dark energy is causing the expansion to be at a different rate. So therefore, both methods are measuring expansion rates at different times, and both possibly could be correct.
Right, that is correct. We just had a little workshop here at Rice, and people talked about this possibility. We had a big conference in Chicago last week, and there were entire days where people argued about this and talked about it. It could be that this discrepancy is pointing us to a deeper theory, a deeper understanding. And we're always interested in finding out new things, which often involve upsetting the current paradigm or model that we have. I would be overjoyed if everything I told you tonight ends up being wrong, if I figure out what is right.
I have two questions. The first one is, what are the chances that the universe has no beginning, and what observations should we do to prove this proof? And could it be that the universe goes through stages like a caterpillar life cycle that goes through stages? And so what would be the observations we need to prove that we are in this stage and that stage?
Okay, well that's a very good question. I think one of the questions I had up should have been, it wasn't, why is there a universe? Did the universe have a beginning? Is the universe eternal? Does it go through something like you described, a big bang and a collapse and a bang and a continuous cyclic universe? And next question. We argue about this and talk about it, but the real question that you mentioned is, how can we make observations to determine it? We haven't figured that out. Why is there a universe? Is there only one universe? Or the universes out there that are outside of our horizon that we don't see, multiverse? And in the conference in Chicago, we had people arguing about that for the evening.
The way we go and we have no observations of anything. So how do you get
in my opinion, not only do we not know how to make the observations, we don't know which observations to make. So that's maybe Einstein is going to have to figure that out.
If the virtual light we can record to get the photographs for 13.7 billion years out is old, where it's virtual. How do we really know that the universe is expanding? Could it be, say, contracting toward the shapely supercluster as toward the great attractor, or something people think that everything's going toward?
Yeah, but as we look out in space, we can measure the relative velocity of galaxies and us. And the galaxies that we see are all receding from us, and every galaxy is receding from every other galaxy. But that's a measurement we make that we're confident about. We're confident that today the universe is expanding.
Also, Rocky, you mentioned in passing a couple of times the possibility of probing the universe beyond the epoch of accommodation, this customary background veil using gravitational waves. Do you want to maybe elaborate on that a
Well, I could elaborate on it because gravity is a weak force. Gravitational waves can go through material of densities that light cannot. And people, if you're really interested in this exciting idea, at 4 o'clock tomorrow, there'll be a talk here, and everyone should go attend it.
Stay tuned.
I have two questions, may or may not be related. First, can dark matter be converted into dark energy? Because he kind of set up this mechanism between the two. And then the second question is in terms of your final states, so, you know, the expansion and the collapse from the point of view of classical thermodynamics and entropy. The entropy of those final states is very big. Should the second law have anything to say about this entropy?
Yeah, so the first question was, could dark matter and dark energy be the same thing? Yeah, it's a very attractive possibility. And it would be really a beautiful result if they would turn out to be the same thing. And people have tried to come up with ideas and concepts how they could be the same thing, or different aspects of the same thing. To me, they are not convincing ideas because none of them are mine. Now, in terms of the ultimate fate of the universe and entropy and things like that, entropy is a little bit more complicated when gravity is involved than if it's just thermodynamics. So that's a very deep question that it's a very good question that I could answer given a half hour and a couple of equations. But you know, it's a good question, but entropy is more complicated once gravity is in the game.
I'm sorry, just like that, I guess, one to bed before too late, so I'll have one more question.
On your pie chart of everything and nothing, I was wondering, is there a place you can put the cosmological constant? Is it the dividing line between dark energy and dark matter, or?
Well, we think one explanation for the acceleration of the universe is dark energy, and the leading explanation, which doesn't mean it's right, of course, for dark energy is the cosmological constant. So that 70% or so slice of the universe that I wrote as dark energy is the cosmological constant in the way I presented it. It may turn out, I would love to see that turn out to be wrong, but I've been trying to show why it's wrong, but it's the best explanation we have now. So I spent an hour telling you about things I don't know, the nature of science. So thank you very much for coming out.